All right. So the purpose of this presentation is to give you an overview of the research and education activities that we have carried out at K-State and partner universities in the past 2 years. So I'll just, this is the overview of my presentation. So I'll give you a little bit of background on CMCs, how we got involved in this research, why it's important, and then move on to the research outcomes from K-State, which is going to be the primary focus, and I'll give you a bit of a summary of the activities going on at partner institutions within the US. This will be followed by a couple of slides on the benefits of international partnerships, and then I'll move on to the broader impacts, which, because it's an NSF, National Science Foundation supported project, this is a very important aspect of it. And so I have a couple of slides on the PIRE workshop from previous years, and some results from the survey, and then how it has allowed us to improve our partnership with industry, aerospace industry. And then I have some slides on education impact on students, both graduate as well as undergraduate students. And I'll conclude with the milestones. Just one slide just to show you what we have been able to achieve and what remains to be done. So why CMCs? If you're following this research topic, CMCs, you may have noticed that the number of publications on this topic has increased considerably in the past 5 to 10 years. And there's many reasons for it. I think one big reason is that these ceramic matrix composites are about 1/3 the weight of nickel-based super alloys that are currently in use in gas turbine engines. Also, the ceramic matrix composites are able to operate at higher temperatures than nickel-based super alloys, so about 200 degrees C higher, which means in addition to saving weight, you are also able to burn your fuel at a higher temperature, which means better fuel burn efficiency and also lower emissions. And then the CMC-based parts also are able to run hotter, and so they do not require active cooling as is the case with nickel-based super alloys. So that also saves fuel and hence cost. But that's not everything. CMCs have been around for some time. I think another big reason why CMC research is getting attention is the fact that GE in about, I think, 5 to 10 years ago, they were able to demonstrate fabrication of large area CMCs that are able to sustain not only high temperatures but also not fail in a brittle fashion. And so in order to highlight that, I have this video courtesy of GE. So here is a spherical object or a projectile hitting edge of a silicon carbide fiber, silicon carbide matrix composite. And as you can see here, the damage caused by this projectile, which is traveling at the speed of the bullet, is very localized. This kind of behavior was not realized previously. And this kind of deformation is directly related to the proprietary coating that goes on these ceramic fibers. Because of the coating, the interface is made weaker. The interface between the fiber and the matrix is weaker. And as a result, the CMC is not failing in a catastrophic manner, as is the case with ceramics. So this failure here is much more localized and graceful, similar to that of a wood. And it is, I think this is the second big reason why this CMC research is getting attention now. So moving on, uh, fibers are the most common or most desired form of reinforcement in not only CMC but also polymer matrix composite. Long continuous fibers are desired. So for high temperature application for CMC, you have basically two options. You can have oxide ceramics, these are metal oxides, or you can have these non-oxide ceramic fibers, which are generally silicon-based systems. Both of these are able to sustain high temperatures, both possess high temperature capability. However, the silicon-based systems, especially silicon carbide, uh, is has has higher resistance to creep, as shown in this graph here. It's able to sustain higher load for longer periods of time, the same operating temperature as oxide ceramics. However, these silicon carbide fibers or the non-oxide ceramic fibers, they have one shortcoming, which is their high cost. So these silicon carbide fibers are derived from polymeric precursors called carbosilane. These carbosilane are notoriously difficult to manufacture because it's a multi-step process, and then the pre-ceramic polymer need to have a certain molecular structure in order for it to yield phase pure silicon carbide fiber. So that increases the cost, and then the market for the silicon carbide fibers is small compared to carbon fiber. Carbon fibers uh, are selling at $140 per kilogram compared to silicon carbide fiber, uh, which are 18,000 euros per kilogram. Um, and it's because also the market is small compared to carbon fibers. And then the silicon carbide fibers are prepared at 2000 degrees Celsius. So higher temperature, more energy, increased costs. And I would also like to mention that there are 4 companies that are able to manufacture high aspect ratio silicon carbide fibers, and 3 of those are based in Japan. Then, see, the goal of our research objective of our PIRE project is to basically move away from these expensive binary silicon carbide system to multi-component PDCs. So when I say multi-component, I'm talking about silicon, carbon, nitrogen, oxygen-based systems. These multi-component ternary and quaternary systems are derived from organosilicon polymers that are low cost, and some of these actually can be handled in open air, and that reduces the processing cost. And in addition, these multi-component PDCs, SACN for example, or SIOC, the processing temperature is about 1000 degrees C, which is half that of silicon carbide, and that increases the cost as well. So we have 3 research thrust areas, we call them research, and these are loosely based on the way PDCs are manufactured. So thrust area 1 is focused on assessing the suitability of homemade, commercial low cost, or commercial low cost modified pre-ceramic polymers for fiber spinability. So characterizing the molecular structure of the pre-ceramic polymer and assessing the rheological properties, fiber spinability. And then we have research thrust area 2, which is focused on assessing the thermal stability of the aspen fiber during the cross-linking and pyrolysis stages. So here we are involved in establishing, based on our spectroscopy analysis, the cross-linking mechanism or cross-linking pathways, polymer to ceramic yield, morphology of the fiber, chemical makeup of the fiber, And then we have research thrust area 3, which is the ceramic stage. So here we are looking into evaluating the mechanical, chemical, thermal properties of the ceramic fiber at elevated temperatures. We are also looking into the energetics of correlating the energetics of formation, transformation, and decomposition of the PDC fiber by use of high temperature calorimetry. And of course, in addition to all of this, we have a very strong computational component to it. We have collaborators from abroad. We have 5 countries involved and 10 universities from abroad and 3 research institutions. And these participants have been selected based on their expertise in either one or all of the 3 research thrust areas. So, for example, at the bottom, I have listed our project partners from Europe and Japan, and these are experts in polymer chemistry. Majority of them are experts in polymer chemistry, synthesis of pre-ceramic polymers, and also we have experts in melt spinning of PDC fibers and CMCs, testing of CMCs as well. On the US side, those that are listed marked in green, including myself, those are principal investigators with a major role to play in the project. And then those marked in red, they have supporting role in the project. Very important, but supporting role in the project. Okay. I'd like to mention that US universities at the moment do not have the expertise in, or at least when we started the project, in processing of pre-ceramic polymers and also melt spinning of PDC fiber materials. Such expertise exists with our partners in Germany and Japan, and also in France. So these materials were actually pioneered by the Germans and the Japanese. Something to keep in mind. Because it's a PIRE project, the E stands for the education. So we have 3 education themes. So the first education theme is focused on undergraduate research experience, and specifically undergraduate student abroad experience. So the objective here is to create excitement about undergraduate research in general and PDCs in specific. Basically get the students involved early in their degree. Long-term goal is to produce a trained professionals with expertise in processing of pre-ceramic polymers and non-oxide CMCs. And the second education theme involves the PIRE workshop and development of coursework related to polymer-derived ceramics. And this is designed to increase the scope of PDC research, okay, and education. And then we have education theme number 3, which involves reciprocal visits. So graduate students from US traveling abroad, or we are hosting graduate students from partners in Europe and Japan. And the idea here is to co-supervise students and publish joint papers. That's the short-term goal. The long-term goal is, of course, to have a dual degree graduate program. So the student getting degree from either university. So I'll just talk about move on to the research accomplishments now. So from the Kansas State side, in the past 2 years, we have filed for 2 invention disclosures, one last year, one early this year. And then we have 4 patent applications, either pending or awarded. Actually, 3 patents have already been granted. And these are directly related to polymer-derived ceramic fiber research. Okay, and my graduate student is co-inventor, one of them. Okay. So and then With respect to research presentations or conference proceedings, we got about 8. We got, yeah, probably the number is now higher. This year we got participated in a virtual workshop, but yeah, so about 8 directly related to PDC fiber research from K-State. And then we got 23 others which are not related to fibers, but they're still based on PDC research. Other aspect of PDCs, so 23 of those. And with respect to journal publications from Kansas State University, we have 6 from Kansas State University with graduate student listed as the first author. And I don't have time to talk about everything given the time frame. So I'll just talk about just 2 of these papers, and then my graduate student will describe those in great detail. Okay, so I'm just going to move on. So the first one was a review article, invited review article, which was written by my graduate student Zongkan Ren, and this basically it is kind of highlights the opportunities and also challenges associated with processing and use of PDC materials in CMCs for gas turbine engines. And this was a good exercise for my graduate student who was just beginning to start experiments on PDC fibers, because you need to know what the big picture is before you get involved with the specifics. So this is I believe is a good reading, and I encourage you to take a look at it. And then in your free time, and then next one here is a full-length research article, also written by my graduate student Zongkan Ren here as first author. And then here we have a co-author from France, Crystal Gervais. Dr. Gervais is expert in NMR, and she's our project partner. This is kind of interesting work, so a little bit more on this. Before I get to what this paper is about, I think it's important to mention that many of these multi-component pre-ceramic polymers, are either siloxanes or silazanes. And a lot of these low-cost, commercially available siloxanes are liquid phase at room temperature, and these are essentially oligomers and with viscosity similar to that of water. And so if you try to draw fibers from it in their pristine form, it's just not possible. The rheology is poor, so the rheology needs to be modified. And we can achieve that. There are many ways to do that. One is to heat the pre-ceramic polymer to moderate temperatures, thereby induce some cross-linking, viscosity changes. But then we tried doing that, and what we observed is that this change in viscosity is rather dramatic. So nothing happens up to and 100 and 150, and then all of a sudden around 250, 300, there is a rise in viscosity, and then it just makes this transition from liquid to this glassy solid. There's no insufficient time to draw fibers from this pre-ceramic polymer in pristine form. However, you can modify the chemistry of the pre-ceramic polymer, for example, by reaction with alcohol oxide, and that makes this change in viscosity more gradual. So that's one way. But my graduate student Zongkan Ren, what he did was he modified the rheology of the pre-ceramic polymer by introducing a spinning agent. So in this case, what he did was he selected polyacrylic acid, or PAA, which is an organic polymer. So linear polymer, can be obtained in high molecular weight, and he would add this to the pre-ceramic polymer, in this case silazane, cyclic silazane, at different weight loadings, and then he would draw. That would change the rheology. That would change the viscosity, increase the viscosity by almost 200 times, and then he would draw fibers from it and characterize the fibers using a range of spectroscopy and microscopy techniques. And we, for example, we use Raman to study the evolution of free carbon phase. We use FTIR and NMR to look at to establish the cross-linking mechanisms, and TGA to look at the polymer to ceramic yield. And then based on these analysis, you can propose these kind of mechanisms or make these schematics. We believe that the PAA linear polymer forms a rigid network, and then cyclic siloxane is immobilized in that rigid network. And then during cross-linking phases, the pre-ceramic polymer cross-links via the vinyl groups. And then during the pyrolysis stages, the PAA transforms into the free carbon phase, while the siloxane transforms into SiCN. And more on this will be, this big work has now been taken up by my undergrad student, Porter Harold. So I would ask you to request you to listen to her lecture. She's going to discuss all of what I just said in great detail. But you may notice that this process has problems. One problem, of course, is that we are doing all of this processing in air, which is not a good idea with siloxane, because siloxane react with moisture and produce ammonia, so it's not safe. That's one thing. And then also these ceramic fibers will be carbon rich because of the presence of PAA, which is 48%. And then lastly, these fibers are made through hand spinning, which is extremely time consuming. So now what we are doing is, we have my student, graduate student Zonkan, has moved away from hand spinning and siloxane. He's utilizing siloxanes. And they already have oxygen with, and there's no ammonia to worry about. And he is using electrospinning now. So and he has also looked at other spinning agents. So he's now using PVP, and you can utilize PVP at much lower weight loadings to make the siloxane spinnable. And he's able to make large area 6" by 6" PDC fiber mats. And his presentation is right after my presentation, so he's going to discuss that in great detail. Okay, and also there's a publication coming out on this related to this work, been accepted for publication. And then my other undergraduate student, Maren, she is utilizing those silicon oxycarbide fiber mats and making composite out of them. And she's applying stereolithography to make those SiOC fiber-based composites. So her lecture is going to be on day 4, and she's in fact going to be the first speaker of the day. So I'm going to move on to the research outcomes from partner universities, University of Colorado Boulder. As I just mentioned to you, PDCs are prepared from these siloxanes or siloxanes by heating them to temperatures close to 1000 degrees C. And during this process, many bonds are breaking, many new bonds are being formed. So it's typical of a PDC material to have micropores. And these micropores actually may lead to fracture. So in this work, Rishi and his colleagues from Japan and Italy, these are partners from Italy and Japan, they created these fail-safe maps for PDC. So they would make PDC samples of varying thicknesses and heat them to different pyrolysis temperatures at varying heating rate. And what they observed was that this is the data for samples that were, y-axis is the sample thickness, x-axis is the heating rate, and you see that samples that are thinner than 200 micrometers, they are never failing. They're not affected by the heating rate. And then those that are close to 1 millimeter, they are failing no matter how slow you heat the sample. And that's kind of interesting. And then also they noticed that those samples that were pyrolyzed at 700 degrees C, they did not fail irrespective of the thickness, they all survive 700 degree pyrolysis temperature. And they attribute this kind of behavior to the organic matter that is coming out at different temperatures. So they showed that those specimens that were processed at 700 degrees C, they survived because they did not observe evolution of methane, larger molecules, below that temperature. So the methane along with hydrogen starts to come out at 700 degrees C or higher temperatures, and that is perhaps the reason for failure of these thicker samples. So very interesting work. I think this will have implications in the use of PDCs in CMCs, especially if you're using a pre-ceramic polymer for making a matrix. Okay, so that's interesting work. And then the second one is the experimental setup that is currently that has recently been put up by the graduate students at University of Colorado. So this is inside a glove box. What you see in this schematic is that you can actually have a fiber bundle attached at the top, and it passes through a hot zone, and then you have the other end of the fiber bundle, you have a constant load attached. And you can observe this through a digital camera, and on the other side there is a ruler. So the idea here is that you can basically perform a creep tensile test of pretty much any fiber bundle material. So in this case, they utilized the hand-spun fibers that were prepared by my student, and they subjected those hand-spun fiber bundles to this kind of a test. And what you see here is that on this graph, you have the y-axis is the strain, and the x-axis is the time. And so as you're heating the sample, you observe that first is a positive linear strain, the rise in strain is a function of temperature, and then the sample expands, and then after some certain time, there is a switch. Now you have this negative strain and the sample shrinks. So this, we believe, is delineating two regimes. One is the polymer regime. These were as spun fibers. So we believe that as the sample is heated to elevated temperatures, so it's just it's still in the polymer form. So it tries to expand in the beginning, and then it switches, and once it's ceramic, it's actually shrinks. So it's kind of interesting observation, and we believe that's laying groundwork for a fuller understanding of the polymer to ceramic conversion processes. And the group at University of Colorado has a manuscript submitted. And then we have two graduate students from University of Colorado, and their presentations are after Zonkan's presentation. So I encourage you to attend those lectures if you're interested in knowing more about the research activities at University of Colorado. So Ali is going to talk about polymer to ceramic conversion processes and how he's able to apply machine learning to understand polymer to ceramic transformations. And then Spencer is working on the creep experiments as well as layer by layer deposition of pre-ceramic polymer on silicon carbide fibers to make mini composites and micro composites. Very interesting work. So I'm going to move on, and then our partners in the Northeast here, Lehigh University, Himanshu, as I mentioned, has a supporting role on the project, and his initial focus, in the year one, he basically spent his time establishing protocols for characterizing these hand-spun fibers as well as commercial silicon carbide fibers in X-ray photoelectron spectroscopy. So they have this special XPS which allows you to fracture the specimen inside the XPS under high vacuum and then look at the chemical structure, chemical makeup of the fiber on the surface and in the interior as well. And then they also have a high resolution electron microscope with EDS detector attached to it, so they can get very high resolution images along with chemical makeup of the fiber. And what they observed here is that with silicon carbide fibers is that these 18,000 euros per kilogram fibers are not homogeneous chemically, or neither they are homogeneous physically. In fact, the composition on the surface of the fiber is different than the composition, the interior of the fiber. That's number one. There were many fibers that were porous, and then there were some fibers were outright hollow. Very interesting observation. And we looked at three different commercial silicon carbide fibers, and this is kind of like we see it in pretty much irrespective of the manufacturer. We see these kind of defects in these fibers, which is very interesting. And then Elsa is our partner from MIT. Her research is, she does not have a graduate student on the project yet, and so it's a very small role but very important role. Elsa is involved in looking at the economic and environmental aspect. Remember, these PDC fibers, as I mentioned, they are expensive and the multi-step process. Not only that, but the CMC also, CMC manufacture is a multi-step process and very expensive process, and there's generally a lot of scrap, if you make a mistake. So the ELSA is looking at the economic and environmental aspects, and analyzing the existing manufacturing processes and proposing low-cost alternatives. So she's been involved in data mining, talking to industry partners and partners abroad, collecting information, performing literature, getting information also from published works by other researchers, and then proposing low-cost alternatives to these CMC manufacturing processes, existing processes. Okay. And Alex is our partner from UC Davis. She was at UC Davis and now moved to Arizona State University. She's going to be talking about her research, so I'm not going to get into that, but I'll just tell you that she has she has mentored 4 undergraduate students and 1 graduate student, and she's been highly productive and very supportive of our efforts on the PIRE project. And then Peter Kroll is more with the computational modeling of pre-ceramic polymers as well as the fibers, and he has been super productive. I think he authored like 6 papers on this topic in the last 8 months. So it's just not possible for me to discuss all of that. So he has 4 students presenting at this workshop. I encourage you to attend their lectures. So his graduate student is presenting later today. So please listen to his lecture. Very important work involving carbon morphology, the evolution of the carbon phase during the pyrolysis of the pre-ceramic polymer. Very interesting work, and how that affects the mechanical properties. Okay. And then I'll move on to the benefits of international partnerships. There are many benefits, and especially for us. And I've listed only a few here. One big benefit is access to the high-end equipment, unique expertise. NMR is a big deal for us, and we are collaborating with Professor Gervais. She's able to run samples for us. Not only that, but she's also helping us in analyzing the molecular structure of the pre-ceramic polymers during various stages, crossing and as well as pyrolysis. So that's one big benefit just to me, and then there are other benefits for our other domestic partners as well. And then our undergraduate students are able to travel abroad, get to see how research is conducted at other universities. And we are also able to obtain pre-ceramic polymers that are especially boron modified pre-ceramic polymers, and also photopolymers, pre-ceramic polymers that can be used for 3D printing. That's very helpful from our partners in France. And then we have been able to develop our own experimental setups here in the US with help from our partners abroad. I mentioned electrospinning, and then there's also additive manufacturing. So they've been very open-minded and helping with our research needs. So that's one big benefit. And so obviously, this leads to joint publication. So it's a win-win situation, they call it. And then our graduate student experience has improved because of collaboration with universities abroad, enhances the reputation of our graduate program at Kansas State University. And another benefit of international partnerships is organization of the joint symposium. So it's very helpful in promoting PDC science and also ceramic matrix composite research. So here's a list of some of the symposium or tracks that we have co-organized in the past 2 years. And then moving on to the broader impacts, so this is going to be, this is our third workshop. The very first workshop was held here at Kansas State University campus, and we had 45 attendees. We had researchers from Japan, Germany, France, Italy, and this was the first time that such an international workshop was organized in the engineering department at Kansas State University. So it was a very big deal for us. And we made the workshop open to all students at Kansas State University free of cost. So, and then the second one was held at University of Colorado Boulder, and this attracted more people. So we had 55 attendees, and then more importantly, we had 5 participants from aerospace industry. So like 5 aerospace companies, Lockheed Martin, Cooltech is also involved in CMCs, and then GE and Spirit Aerosystems and United Technologies, and now known as Raytheon United Technologies. So that was well attended, and I have some results from the Qualtrics survey, which clearly shows, if you look at the purple graph here, that the organization of these kind of workshop promotes face-to-face interactions among the PIRE members, also allows our graduate students and undergraduate students to showcase their research finding from the previous years and seek feedback from industry. And so that is one of the goals of the PIRE project. We would like to have this platform made available to all PDC researchers, not just those who are part of the project. And then I'll talk about the graduate students. So University of Colorado gets 2 graduate students, Kansas State gets 1, Lehigh get half a graduate student, and Arlington gets 1, and ASU get 1 graduate student. So this is my graduate student here, Zongkan Ren. He defended his PhD last week, and then I have a replacement for him, Shakir. Shakir has passed his preliminary exam already, and he is all set to replace Zongkan. So he will be involved with the fiber processing, electrospinning, and also high temperature testing of ceramic fibers. And then I co-supervised a student from Italy who was in my lab, Federico Toigo. He was involved with the direct ink write of CMC composites. Very interesting work from Paulo's group. And we looked at utilizing those additively manufactured composites for energy storage applications, in addition to traditional CMC applications. Very interesting work. And then graduate student from University of Colorado, Ali Vadran, mentored by Professor David Marshall, and also supervised by Rishi Raj at University of Colorado. Ali has passed his PhD comprehensive exam. He's been involved in applying machine learning and CT fiber scan to look at the polymer to ceramic transformations and also the mechanics of composite failure. Very interesting work. Ben was a graduate student with Professor Raj, and now Spencer is a PhD student with Professor David Marshall and Rishi Raj. He is looking into additive manufacturing of PDC-based CMCs, including creep testing of PDC fibers prepared at Kansas State University. So again, very interesting work here, interesting collaboration going on. And then University Texas Arlington, Susanna has graduated. She was a PhD student from University Texas Arlington. She worked on silicon oxycarbide aerogels. And then we have a new PhD student from at UT Arlington, Sharik. He's going to present his work, as I mentioned toward the end. And he's been involved in computational modeling of PDC materials. Casey has finished her master's degree. She worked with Alex Navrosky. She performed high temperature calorimetry on the PDC fibers fabricated at Kansas State University. And she also traveled to Germany to work with Gabriel Almera and Rolf Riedel, and also to France to work with Samuel Bernard last summer. And these are the undergraduate students who work with us in year number 1. Some of these have graduated. Isabella worked with me, and then she is now employed at Procter & Gamble. Spencer graduated with bachelor's degree and now PhD student with David Marshall. Sally graduated from University of Colorado Davis. Thomas will graduate this semester, continuing his graduate studies at Lehigh. Kendall is still an undergraduate student at UT Arlington. And these are the students from last year, year number 2. Sophie is a junior in mechanical engineering now. She continuing with research within my lab. Carissa is also an undergraduate student, continuing, hasn't graduated yet, and same is for Henry at UC Davis, and then Jacob at Lehigh. And we hope that these undergraduate students will continue to pursue PDC research. If not PDC research, at least they will go to graduate school and work on a topic related to PDC. And then these are the undergraduate students for this year. So Maren, Ellis, and Porter Harold I already mentioned, and Thomas Egalino continuing with Himanshu, and he's just co-supervised by Donnie Daniels at Kingston University and Imperial College London. And then we have 3 undergraduate students from UT Arlington, Mela Dow, and Jonathan Correa is also working with Professor Peter Kroll, and Jonathan Kroll is also working with Professor Peter Kroll and also with Professor David Marshall at University of Colorado Boulder. And then we have 2 undergraduate students at ASU working with Professor Alec Navrosky and co-supervised by Professor Gabriel Lamera at TU Darmstadt. You will hear from them on day 4. Milestone chart, just very briefly. This is the chart that we submitted at the time of proposal writing. This is just to show you where we are and where we want to be. So we have made significant progress in processing or understanding the molecular structure of various, we have studied close to 20 different pre-ceramic polymers, some homemade, some commercially obtained, but all low-cost pre-ceramic polymers. And we are at a point where we can make fibers from them. We are at the moment, we are involved in high temperature testing of these ceramic PDC fibers, and my graduate student will discuss some of that in his talk. And then education activities are, I think, on track. Actually, we have done a lot more than what we had proposed at the time of proposal writing. We have introduced 3 seminar-based courses and 1 lab-based modules related to PDCs materials. And then, I think there's some new opportunities have come up. For example, use of PDCs or pre-ceramic polymers to make a matrix for CMC. So especially if you have a pre-ceramic polymer that with a high polymer to ceramic yield, something that you can handle in open air, I think that will be very useful. So we're looking into that. And then there are some challenges as well. Graduate students, generally the graduate students are international students. At least in our case, we have 50% of the students are graduate students. And sometimes it's challenging for them to obtain access to a national lab. But that's a minor concern, and it's very manageable. So with this, I come to the end of the presentation. Thank you very much for your time. So, and the questions will be discussed toward the end, will be answered toward the end. Okay, thank you.